Hi, this is Dr. Wooten, and this presentation is on the classification of number sets. Enumeration is used for ordinal counts and quantifying cardinal counts. The concept of enumerating 1, 2, 3, so forth and so on can be traced back to shepherds tying knots in rope to keep track of their sheep as they entered the open fields to graze. Thus, enumeration leads to the creation of the set of natural counting numbers. Here the set is denoted by the double-lined letter N, and the elements are offset with braces and listed in roster notation. That is, the elements are listed one at a time, where the three dots indicate to continue in the same fashion. As the sheep returned in the evening to the fold, the shepherd would untie one knot for each sheep as they entered. If there were knots left in the rope, then the shepherd knew that there were sheep in danger that he had to go find. And when there were no knots left, this led to the concept of a zero count, leading to the formation of the set of whole numbers. The natural set of numbers is a proper subset of the set of whole numbers. The only difference between these two sets is the element 0, yet they have the same cardinality. Both sets are countably infinite. That is, there is a one-to-one correspondence between the elements of the set of whole numbers and the set of natural numbers. Giving direction to the set of natural numbers, multiplying by -1 gives the values in the opposite direction and gives rise to the set of integers. Therefore, the interpretations are: positive indicates values to the right of 0, and negative indicates values to the left of 0. Hence, multiplying by a negative is equivalent to rotating 180 degrees about the point of origin. Thus, negative times negative is positive. Negative times negative times negative is negative. In general, any even power of a negative is positive, and any odd power of a negative is negative. While the size of the integers appears to be nearly twice that of the size of natural numbers, they in fact have the same cardinality. Both sets are countably infinite. That is, there is a one-to-one correspondence between the elements in the set of integers and the set of natural numbers. The set of rational numbers is the set of integers taken in ratio, making sure that you do not divide by 0. These quotients are denoted by the double-lined letter Q. The set is stated here in set builder notation. That is, the elements are not listed, but rather a description is given on how to construct the elements. The set of irrational numbers is the set of those real values that cannot be written in ratio, like the square root of 2, pi, and e. The set of irrational numbers is the complement of the set of the rational numbers, with respect to the universal set R, that is the set of real numbers. The set of rational numbers and irrational numbers form a partition of the set of real numbers. That is, these two sets are mutually exclusive and in union form the entire set of real numbers, where two sets are mutually exclusive if their intersection is the empty set. The set of complex numbers, denoted by the double-lined letter C, are the numbers of the form a plus b, where a and b are real numbers, and I is the directional component perpendicular to the real number line. Below is the Venn diagram illustrating the relationship that exists among the various sets of numbers. The set of natural numbers is a subset of the set of whole numbers. The set of whole numbers is a subset of the set of integers. The set of integers is a subset of the set of rational numbers. The set of rational numbers is a subset of the set of real numbers, and the set of real numbers is a subset of the set of complex numbers. The set of real numbers can also be illustrated using graphic notation. The set of real numbers can be represented by a line that extends from negative infinity to positive infinity. Given 0 as the point of origin, positive values lie to the right and negative values lie to the left. Hence, a multiple of -1 is equivalent to rotating 180 degrees about the point of origin. Therefore, the direction I is equivalent to rotating 90 degrees counterclockwise about the point of origin. Moreover, given the value in the direction I perpendicular to the real number line goes up from the point of origin, By multiplying by -1, this gives the imaginary direction -I, perpendicular to the real number line, going down from the point of origin. Therefore, there are 4 directionals in the complex plane. I is indicated usually by the square root of -1, where I times I is -1, I times I times I is -I, and I times I times I times I is +1. Furthermore, I to a power of a positive integer rotates counterclockwise, whereas I to the power of a negative integer rotates clockwise. Therefore, the set of values of the form a plus bi create the complex plane.